Hi guys, in the last lecture we solved some problems based on single phase transformer. So in this lecture we'll continue from there and we'll see some more problems based on single phase transformer. So let us start up with our first problem. The figure shows an ideal 3 winding transformer. The turns ratio are N1 is to N2 is to N3, 4 is to 2 is to 1. Okay. Resistance of 10 ohm is connected across winding 2 and capacitor of reactance 2.5 ohm is connected across winding 3. Now the supply to winding 1 is given as 400 volt and the supply voltage phasor is 400 angle 0. We need to find supply current phasor I1. Okay. There can be several methods to solve this problem. Either you can find out the current in both these loads and then transform these currents to the primary. That you can do. Or better, if you want a shorter solution, then you must transform these impedances to primary and then calculate the current. Okay. So I am transforming these impedances, then R dash will be given by R into N1 by N2 whole square. That is 10 into 2 by 1, or 1 minute, it will be 4 by 2. 2 by 1 means 4 by 2, N1 is 4, N2 is 2 square, that is 40 ohm. Similarly, if we transform XC dash, it will be XC into N1 by N3 whole square, that is XC is 2.5, N1 by N3 will be 4 by 1. It is 40 ohm. Now if we construct the equivalent circuit, here we will have a source, then we will have a resistance, that is R2 dash 40 ohm, then we will have a capacitance, that is minus J 40 ohm. This will be 400 angle 0. Now we will have two currents, I1 and I2. I1 will be 400 angle 0 by 40, that is 10 ampere. I2 will be 400 angle 0 by minus J40, that is 10 J ampere. So it implies I, which is the supply phasor, is I1 plus I2, which is equal to 10 plus J into 10 ampere. So this way my effort is lessened when solving this problem. Otherwise what you can do is you can calculate I2 and I3 dash, I2 and I3, that is the currents in the resistance as the capacitance. Then transform those currents to primary and then you can add those currents to obtain the supply current. That is how you can solve this problem. Otherwise the other method can be calculate the power in resistance, calculate the power in capacitance, and then add those power. The same power will be supplied from the source. From that also you can calculate the current. So whenever we talk about 3 winding transformers or questions based on finding the supply current and all, there are many methods referring the impedances, referring the current, referring the voltage, or equating the power. So it is your choice which method clicks to you first of all, that you can follow. None of the method is good or bad. In our next problem, we have been given a core of a 2 winding transformer which is subjected to a magnetic flux as shown. We need to find the variation of EMF. Okay, we need to find ERS. Now, if you see, the flux going into the core of the transformer is something like this. Now I know the secondary flux should oppose primary flux. So secondary flux should be upwards. For having the flux upwards, the current direction should be like this. Okay. We know that the secondary always delivers the current. Primary absorbs the power and secondary delivers the power. That means this terminal should be positive and this should be negative, because for delivering the power, current must come out of the positive terminal. So S will be positive, R will be negative. That is, the terminals have been marked as opposite. So what to do in such type of problems? First of all, you need to find the positive and the negative terminals. How to do that? The secondary flux will always oppose the primary flux. Based on that, you will find the current direction. then current will always come out of the positive terminal of the secondary and it will go into positive terminal of the primary. Okay, that way you can identify the positive and negative terminal. Then EMF magnitude, that is, it will be N into d phi by dt. Simply. Okay, after identifying the polarity, just calculate the magnitude. Since I know polarity given in the problem is opposite, so what I will write? ERS is equal to minus N d phi by dt. If we were to find ESR, I would write N d phi by dt because the polarity assumed is same as the polarity due to flux. In our question, the polarity given ERS is opposite to what we can find out using the flux. Hence, we have to use a minus sign. Okay. If we calculate the slope in this region, it will be 0.12, 0.12 divided by 1. In this region, 0.12 by 0.5 minus 0.24. And in the middle region, the slope is 0. So, if we write down ERS, okay, if we draw ERS, the terms are 200, 200 into 0.12 is 24, but it is with a negative sign. So, it will be minus 24 up to 1 second. I have just multiplied 0.12 into 200 into minus sign. Then 1 to 2, the EMF induced is 0. Then 2 to 2.5, since slope is minus 0.24 into 200, that is 48, and with a minus sign, minus will become plus. So it will be plus 48. This will be the waveform for ERS versus time. Okay, just remember, first find out the polarity of induced EMF using the Lenz law on the flux, then calculate the magnitude of EMF using E is equal to N d phi by dt, that is the Faraday's law, and plot the waveform. In our next problem, it is showing a two-winding lossless transformer with no leakage flux. No leakage flux means leakage reactance is 0. Lossless means resistance core and resistance armature, or let us say resistance winding, is 0. Core resistance and winding resistance both are 0. Is excited from a current source IT whose waveform is shown. Magnetizing inductance is 400 by pi millihenry. We need to find peak voltage across A and B. Since this is 1:1 transformer, primary voltage will be same as secondary voltage. So if we draw the circuit, since we are neglecting all parameters except magnetizing inductance, referring the circuit to primary, since secondary is open circuited, primary will also be open circuited. This is given as 400 by pi. Okay. Now, since this current IT is going, it will entirely go into this inductance because the other terminal is open circuit. So entire current flows through the inductance. Now voltage across a inductance will be L into di by dt. This will be the voltage. So let us calculate di by dt from here. X terminal is 5 millisecond, Y is 10 ampere. 10 ampere by 5 millisecond. So voltage will be 400 by pi into 10 raised to power minus 3 into 10 by 5 into 10 raised to power minus 3. Okay. So it will be 800 by pi volt. Okay. And since we are taking derivative of the current, the voltage waveform will be a square wave. That is initially positive, then negative, then positive, negative. So whatever voltage we are driving is the peak voltage. This will be 800 by pi. Other peak will be minus 800 by pi. Okay. This will be the waveform for the voltage across the inductor. Okay. So if we plot flux and voltage on the same axis, flux is something like this. So whenever flux has a positive slope, the voltage across the inductor will be positive, then it will be negative, then positive, then negative. Okay, this waveform will be 800 by pi volt. So that is how the waveform will vary. That is, the square wave will be induced across the inductance or across the secondary winding. Let us see the next part of the same problem. Now the current waveform is replaced by this and switch is closed. That is, now the circuit is not open. So if we draw the equivalent circuit, this is my current source. We have a magnetizing reactance and then we will have a resistance because secondary is now closed. This is my 30 ohms. Okay. And now since we are using a sinusoidal source, we will convert the inductance into reactance. So it will be 400 by pi L into omega. Omega is 100 pi. So it will be 40 ohm because this is in millihenry. Okay. Now we need to find the voltage. Current is given as 10 sine 100 pi t. So if I want to find the current in resistor, IR would be 10 into J40 divided by 30 plus J40. So it will be 10 into 40 is 400 by 50, that is 8. Angle, it will be 36.86 degrees. Okay, if you solve it in calculator, it will come out to be this. Then if we calculate voltage across the resistor, 8 into 30 will be 240 volt. Now since the transformation ratio is 1:1, the same voltage will be appearing across the secondary winding. So the peak voltage across A and B will be 240 volt this time. So remember, when we have closed the switch, then we need to bring the secondary impedance to the primary to calculate the voltage. In our next problem, it is showing two transformers in cascaded configuration which have transformation ratios of A and B. It is given that Zn impedance is resistive and equals 2.5 ohm when network is excited with a sine wave of angular frequency 5000 radian per second. That is, if we transfer the entire circuit to the primary, the input impedance is resistive and it equals 2.5 ohm. So first transfer this circuit to here. So it will be like this, and this resistance will come here. How much will this resistance be? 2.5 by A square. This is 1 millihenry, 10 microfarad. Then if we transfer the entire circuit to the primary, it will be like this. It will be 10 microfarad, 1 millihenry by, it will be A square. This will be 2.5, sorry, it will be B square, 2.5 by A square into B square. I am just using the turns ratio square to transform the impedances. Now it is saying that the input impedance is resistive. That means the inductor and capacitor should cancel the effect of each other. That is, 1 by omega C must be equal to omega L. Then they will cancel the effect of each other. Omega C, we rub this. Okay. So 1 by omega is given 5000 into 10 raised to power 10 into 10 raised to power minus 6. Omega L is 5000, L is 1 millihenry by B square. When it has been transferred into primary, we will have a factor of B square. If we solve from here, B square comes out to be 0.25, which means B will be 0.5. Now the input impedance remains only resistance. So resistance in the primary circuit was 2.5 by A square B square, but it is saying input impedance is 2.5 ohm. That is, A square B square is 1. That is, AB is equal to 1, which implies A will be equal to 2. Since B is 0.5, A will be equal to 2. So that is how we calculate the transformation ratio of each of the transformer. Moving on to our next problem. Again, we have been given a 3-winding transformer which is connected to a AC voltage source. The number of turns are 100, 50 and 50. If we are neglecting the magnetizing current, I2 and I3 are given, we need to find the current I1. Okay. So let us transform I2 and I3 into the primary winding. I2 dash will be I2 into N1 by N2. So it will be I2 is given as 2 angle 30 into N1 by N2 will be, it will be, since currents are transformed in the opposite ratio, so take care N2 by N1. And remember, the easier way to remember this is MMF of the primary will be equal to MMF of the secondary. So this will be 1 angle 30 degree. Now I3 dash will be I3 into N3 by N1. So it is 2 angle 150 into 50 by 100, that is 1 angle 150. Now total current will be I2 dash plus I3 dash, 1 angle 30 plus 1 angle 150, it gives 1 angle 90 degree ampere. Okay. So this will be the current flowing in the primary winding due to the secondary and the tertiary winding, or due to the two secondary windings of the transformer. Moving on to our next problem, it is given a 11,000 volt 50 Hz transformer has a flux density 1.2 Tesla and core loss of 3000 watts at rated voltage and frequency. Now linear dimension of core are doubled, primary and secondary turns are halved. New transformer is energized from 22,000 volt 50 Hz supply. So if you see, frequency is constant. One observation I can make. And V2 by V1 is 2. Voltage has been doubled. Turns ratio or the turns have been halved and dimension has been doubled. Transformer have same core material. Same core material implies that the same hysteresis coefficient and the same Steinmetz exponent and the same lamination thickness, that is the same eddy current losses. Core losses of the transformer are, okay. So let us first find out what happens to the magnetic flux density. Now we know voltage is equal to 4.44 Fn Bm into area. So Bm2 by Bm1 will be, since frequency is constant, V2 by V1 into N1 by N2 into A1 by A2. Okay. So V2 by V1 is 2, N1 by N2 is half. Okay. So saying the turns are halved. Now the next thing it is saying is that N1 by N2 is 2. N1 by N2 is 2 because N2 by N1 is half. Now since dimensions are doubled, so area will become 4 times. So A2 by A1 will be 4 and A1 by A2 will be 1 by 4. So it will be 1. That is, magnetic flux density is also constant. Okay, now we know hysteresis loss is proportional to Bm raised to the power x F into volume. Now Bm is constant, frequency is constant, so hysteresis loss will be proportional to volume. Since dimension becomes double, the volume will become 8 times. So pH2 by pH1 will be volume 2 by volume 1, that is 8. So the new hysteresis loss will be 8 into 3000, that is 24,000 watt. Okay, that will be the hysteresis loss in the new transformer. Okay, so I will assume that the core loss is dominated by the hysteresis loss, so I am neglecting the eddy current loss contribution here. So remember, whenever we are talking about core loss, how does it change? Then you can neglect eddy current loss if you are not able to separate the losses into eddy current and the hysteresis loss. You can assume that only hysteresis loss is present. Okay, if you are able to separate, then only scale both the losses, otherwise scale only hysteresis loss. Next is for determination of losses in a transformer having a 400 volt 50 Hz using test, the total iron losses were found to be 2000 watt. Okay. So 400 volt 50 Hz, total iron losses are 2000 watt. Then we have the iron losses to be 750 watt when voltage is 200 and frequency is 25. So if we take initial V1 by F1, that is 400 by 50, which is equal to 8. Then if we take V2 by F2, that is 200 by 25, which is also equal to 8. Since V by F is constant, both are 8, we know hysteresis loss will be proportional to frequency and eddy current loss will be proportional to frequency square. Okay. Then if we take the equations, initially pH plus PE I can write down, the total core losses was 2000 watt. Then since frequency is halved, hysteresis loss will be halved, so 0.5 pH. Frequency is halved, eddy current loss will become 25% PE. This becomes 750 watt. Now if we solve this, we will get hysteresis loss to be 1000 watt and eddy current loss to be also 1000 watt. So that is how you separate the iron losses into hysteresis and the eddy current losses. And wherever you are not able to separate like this, you have to consider only hysteresis loss. So let us move on to our last problem. It is given a 20 kVA 2500 by 250 volt 50 Hz transformer gives the following test result. We have been given open circuit test and short circuit test. Now it is asking the power factor if the transformer operates at maximum regulation. We know for maximum VR we derived phi was equal to tan inverse, how much it was? X01 by R01. So we need to find the series parameters of the transformer circuit. Series parameters can be determined using short circuit test. First of all, let us determine R01, that is 320 by 8 square, that is 5 ohm. Then Z01, which is 104 by 8, that is 13 ohm. Then X01 will be under root Z01 square minus R01 square, which is 12 ohm. So phi will become tan inverse, how much? 12 by 5. So to calculate the power factor, we will take cos phi. Cos of phi will become base upon hypotenuse, that is 5 by 13, that is 0.384 lag, because maximum voltage regulation occurs at a lagging power factor and zero voltage regulation at a leading power factor. So these type of questions can come in the GATE examination. We have covered all the concepts that we saw in the theoretical lectures. So we have covered numerical problems based on all. In the next lecture, we will be starting with our three-phase transformers, and their phasor diagrams are very much important from GATE point of view.